So here's a definite integral, and we want to try to find the value of it. We should try to think briefly about whether or not this is an improper integral. Does the fundamental theorem of calculus apply to this directly? And I think you're going to realize that it does. This x squared is obviously always defined, as is cosine of x, so we don't have to worry about it ever being undefined at or between the limits of integration. So we're going to be looking for an antiderivative of this integrand. Once we have that, we'll toss in the upper limit, toss in the lower limit, take a difference, and we're going to have our answer. So now it's a matter of trying to figure out how to evaluate for the antiderivative. How do we find the antiderivative of this? Well, we don't have an integral formula for the antiderivative of x squared cosine of x. We don't have the luxury of a substitution being easy or obvious. We can't really let u equal anything here and get the proper cancellation to occur. This integral is a product, right? And when an integral is a product, what will work a lot of the time in order to evaluate is if you try to use integration by parts. So we're starting with an integral that's defined to be u times dv. And what we're going to do is we're going to assign u, we're going to assign dv, and then we're going to be responsible for computing what v and du are, and the formula for integration by parts will then be able to be constructed. So we have uv minus the integral of v du as that formula for integration by parts. So we're attempting to use this. Now, what I always like to use as a little trick to try and figure out what I should let u equal, because that's my next job. If I'm trying to use integration by parts, I've got to assign u, and I have to assign dv, and I have to make sure I do this the right way, or else I might not get to the point where I eventually have an integral sitting here that I can actually evaluate. So I like to use this little acronym, ILATE, and the letters in this acronym represent different types of functions: inverse trig functions, logarithmic functions, algebraic functions or polynomials, trigonometric functions, and exponential functions. And the closer something is to the front of this acronym, the more likely that's to be let equal to u. So we have an algebraic piece within this integrand and a trigonometric piece. Following the acronym, algebraic is before trigonometric, so I'm going to let u equal the algebraic piece, and I'm going to let dv equal the trigonometric piece, which is cosine of x, and the dx is going to be attached to that as well. Now our job is to figure out what du equals. There's a du right here, and also to figure out what v equals. There's a v here and there's a v here. So we're basically trying to build the right side of this formula right now. So we're going to find our du by doing the derivative of u with respect to x. The derivative of u with respect to x is going to be 2x. So what does du equal? Well, if I just multiply both sides of this equation by dx, that's what du equals, right? Du is going to be equal to 2x dx. What does v equal? Well, to undo the differential, I'm going to have to do an antiderivative. The antiderivative of 1 with respect to v is going to be v. And then the antiderivative of cosine is going to be, whoops, not cosine, but sine. Antiderivative of cosine is sine of x. I don't have to put a plus c here. It's a definite integral anyhow, so eventually we're going to be getting a numerical value for our result. So you don't really have to worry about the plus c in this definite integral, and you don't have to worry about it in this intermediate antiderivative when you're using this process, integration by parts. So let's see. We're going to be transforming our original integral by constructing the right side of this formula. So now I need to write out u times v. So that's x squared sine of x. So u times v minus the integral, right? Minus the integral of v, which is sine of x, du. So du is 2x dx. I'm going to put the dx here. I'm going to put the x in front of the sine function, and then I'm actually going to factor the 2 out in front of that integral. Okay, so there's my first application of integration by parts. The reason why I say first is because you notice we still have a product here. If I apply integration by parts one more time and let u equal x, this piece is eventually going to become a constant, and we'll be able to finally evaluate our antiderivative. So we're going to go through a second application of integration by parts, and I guess I should kind of denote that this is a definite integral. Whatever this antiderivative turns out to be, I'm going to have to toss in these limits of integration and take a difference. But we're not ready to do that just yet because we haven't found an antiderivative for this piece. So we're going to let u equal, following the acronym again, we have an algebraic piece, we have a trigonometric piece. A is closer to the front of this word than t is. So we'll let u equal x. And then the derivative du dx is going to be 1. I'm going to multiply by dx just like we did a minute ago. So du is equal to 1 dx, or du equals dx. And then dv is going to be equal to sine of x dx. So to undo the differential, to make the differential go away, you're going to integrate. And the integral of 1 with respect to v is going to be v. And the integral of sine is going to be negative cosine of x. And like we said before, you don't have to worry about a constant of integration there. We're going to use this round of integration by parts to transform this integral that we still couldn't do that involved that product. So I'm looking back at this line. This was already out of the integral, so I'm just going to have to copy that stuff down as it was back here, minus 2, but then I'm replacing the integral with another application of integration by parts. So the integral of x sine of x is going to be replaced with my new u times my new v, so that's going to be x times negative cosine of x, so I'm going to write that as negative x cosine of x, minus the integral of v, right, minus the integral of v du. So v is negative cosine of x. I'm going to factor that negative out in front of my integral and change this minus sign to a plus sign. And then I have cosine of x sitting inside of this, and a dx there as well. This is now an antiderivative that we can evaluate. This is now something we can manage with. Once we do that integral and write out our next line, we're still going to have to remember we were dealing with a definite integral initially. We're going to have to evaluate that at pi by 2, evaluate that at 0, and take a difference. So one more line here and we'll finally be able to do some evaluation. So x squared sine of x plus, so I'm distributing at this point, plus 2x cosine of x, right? Negative times negative gives me a positive there. And then I'm going to distribute this negative 2 into this piece as well. So minus 2 times the integral of cosine of x. Well, the integral of cosine of x is sine of x. We don't have to worry about a plus c. We're using the fundamental theorem of calculus here to evaluate a definite integral. So we're going to toss in this limit of integration, then toss in this one, take a difference, and have our answer. So when we put pi by 2 in place of all the x's, we're looking at pi by 2 squared times the sine of pi by 2 plus 2 times pi by 2 times the cosine of pi by 2 minus 2 sine of pi by 2. So when we put in the upper limit of integration, we get this. We're going to have to evaluate this in just a second. What happens when we put in 0? Well, putting in 0 is a lot nicer. You put a 0 here, it's 0 squared times sine of x. That first term is 0. You put a 0 here, 2 times 0 times cosine of 0. That next piece is 0. When you put a 0 into the sine function in place of that x, you do have to be a little more careful with that. You don't want to assume that's a 0 right away. You're going to want to think about what the sine of 0 is. Eraser work. There we go. So sine of 0 is something we're going to have to evaluate in a second here. Now it's time to do some work with the unit circle, right? So here's our unit circle. Circle radius 1 centered at the origin. Every point on the unit circle has coordinates cosine of theta, sine of theta. So the x-coordinate gives cosine of an angle, and the y-coordinate gives sine of that angle. We need to evaluate sine of pi by 2 and cosine of pi by 2. Here's the angle pi by 2. The x-coordinate of that point is 0. The y-coordinate of that point is 1. Cosine corresponds to this x-coordinate. Sine corresponds to this y-coordinate. So sine of pi by 2 is 1. So that means this first term is going to be pi squared over 4, right? I'm squaring pi by 2 there, times 1. So I'm not going to put the times 1. I'm just going to leave pi squared over 4. And then plus 2 pi over 2. Well, that's going to cancel with that. And then cosine of pi over 2. Well, that's going to be the x-coordinate of that point from the unit circle. So that piece is actually going to drop out. We're going to have pi times 0. Cosine of pi by 2 is 0. And then minus 2 times sine of pi by 2. Well, we said a minute ago that sine of pi by 2 was 1. So this first quantity boils down to pi squared over 4 minus 2. And then if you think about the sine of 0, here's the angle 0. The coordinates of that point in the plane here are 1, 0. We're looking for the sine of 0. That's going to correspond to the y-coordinate of this point, and the y-coordinate of that point is 0. So everything here becomes a 0, And our definite integral has a value of pi squared over 4 minus 2.